To hear me clearly? Hi Abhay, hello Atul, hello Lakshmi, hello Mahesh, hi Mamta, hi May, hey Midhili, hi Prezi. Yes, we are just about to start. Can I make one of you as co-organizer so that one of you can also record the session in case something goes wrong with my machine? At least we'll have a backup. Yeah? All right. Sure, yes. Let me try to create a chat group. Okay. Abhay, I'm making you the organizer because you're the first one in the list. Okay. So, all right. Now, can you start recording? All right. Great, great. All right. So, let's start with our discussion. We are 6 minutes past our usual time. All right. So, there was somebody who had some question before we started. All right. So, it was Mahesh's question. Mahesh was saying, while waiting to start, I want to check on the following. It has been long time since I've programmed, and I mostly use Mac. I do not have programming tools. Appreciate if you could walk through. All right. So no worries. So all right. So no worries. As we go forward, I will help you. I'll help you with the setup. All right. All right. There is a quick question from Yash. Can we use Scala also in Hadoop? So when we talk about Hadoop streaming, we will talk about Scala as well. We will show you that any programming language can be used as MapReduce. All right? No way. Good, good. All right. So I will do a quick recap of yesterday's discussion. The quick recap is one, the data is inevitably growing from all aspects, and as the data is growing, the traditional computing is not able to catch up. Okay, while the data is an asset in the sense that using data you can do a lot of work where the where the machine learning kind of predictions are only possible with huge data, and even a simple statistical analysis is very valuable if the data is big. But how to do that analysis, how to do how to handle such kind of data? Also, the other use case that we will discuss during HSpace is, since the number of requests grow as the company becomes popular or your product becomes successful, the technologies or the computing is not able to catch up, as a single computer is not able to catch up with number of requests that come in, and that's why you require solutions like HBase to handle that kind of load. Okay, so the summary is, the as data grows, single computer cannot catch up. That is why we need new kind of tools such as Hadoop and others to handle the load and to handle the computing requirement. by the way of multiple computers or distributed computing. All right, so that's what we discussed yesterday in first half, and then we went through the overview of Hadoop. Okay, the various components, the main elements of the ecosystem. Now today we are going to start the HDFS from beginning, because some of you uh, told me that it was not good enough. So I like to start from the beginning in the correct way, all right? Because it was little too fast yesterday, the the HDFS part. All right, good, good. So feel free to ask questions. I mean, whenever it comes, I'll explain to you whenever I get some time. All right. In today's class, I'm going to discuss the HDFS and the uh, if time permits, we will move on to the architecture of Hadoop 1.0 and Yarn. Also, we will talk about the infrastructure. Okay, so let's start with the HDFS. Okay, so the first and foremost is storing data in the form of files and folders. Probably, as you started with the computing, that could have been your that could have been your first interaction with the computer, right? There's some data stored somewhere, and you want to start, you want to use it. So, so the storage is probably a very important point to start with. Okay, so and all of the components in Hadoop, be it Yarn, be it anything, they all depend on HDFS. Okay, all right. Here's a question to all of you. Let's say let's say you live in a hostel or you live in a society where all of you decided that you will build 100 terabyte movie storage so that all of you could store the movies and watch it on your local network. How would you store such kind of data, or how would you build such kind of storage? Okay, yes, I'm expecting answers from you. You have 100 terabyte of data and you want to do this. You want to store 100 terabyte of data, and or you can say that you are speculating that you will require 100 terabyte of storage for storing movies. So you want to build an storage. So remember the days when I mean, if you are from a kind of hostel background where you wanted to share the movies, watch it, or even in your organization, wherever you're working, you would have these requirements that we want to store hundreds of gigabytes in somewhere. But here, the need is to store hundreds of terabytes. What are you going to do? Yes, he's saying store the data in tapes. Okay, okay. So tapes are a little costly, and tapes are mostly kind of slow to read from. Why not in normal hard drives? Yes. Okay. So we have Mahesh's answer. Mahesh is saying create 9 to 10 NAS shares. Okay. Okay. Good. Good. Okay. Anybody else? Yeah. Yes, his point is that we should use tapes because hard drives are limited by the capacity, but so is tape drive as well. Tape drive just I'm not even sure how big are tape drives, but I'm very sure that tape drives are also limited by the capacity. Okay, okay. Anybody else? So you want to build basically kind of a movie storage in your local network such that you can store hundreds of terabytes of movies and everybody can watch. Midil is saying we can use a server with big storage. Okay, and store on local drive and share the location with user to access it. Okay, okay, okay. Yes, this point is we can create a network of everyone's personal computer and store files. Okay, that's also interesting way of looking at it. And Prezi is suggesting that we should have NFS mounts. Good, good. Okay. Amta says the network attached storage. Okay, brilliant, brilliant. And Abhay says that store them alphabetically on different hard disks on the network, and 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 store them multiple hard drives in the network. Brilliant, brilliant. So that's a very good answers. All right. So yes, let's go with those of you who are. I mean, most of you are talking about, I think, the same model. So I mean, honestly, this is how we did things in 2002. This is how we did things. So we did what we did in earlier. So at Disha, we had our sysadmins used to provide us network attached folders to everyone. So what we used to do is to provide a massive amount of storage for the users. What we did was we basically bought lots of computers, lot of hard disks, and connected these computers in the network. And after we connected them in the network, we shared their drives so that, or shared their drives in the network. Now, on few computers, we created this kind of architecture where all of these hard drives were mounted. We created kind of a network mapping, okay, such that when you look at this folder called main folder, we just created a folder called main folder. If you look at that folder, under which there will be one folder each for all the hard drives in the network. So if we bought 101 terabyte hard drives and made hundreds of folders and mapped them, now we had this place where we could store things. And then after we had done this, we created a schema. We created kind of, you know, guidelines to all of the people saying store all the movies starting with A in drive 1, store all the movies starting with B in drive 2, and so on. So these are the kind of things we used to do, or these are the kind of storages that have been done in past. So, my question to all of you is, do you see any problem with this architecture? Do you find anything wrong with it? Yes? So, is this clear how, what we did here? So, we basically created one folder one folder in one machine, and under which we created subfolder, and these subfolders were nothing but they were kind of link, or they were kind of symbolic representation of a hard drive in the network. Okay, so this main folder was having these many shortcuts or links to the or network maps to the to the various hard drives. Okay, and we did this on, say, 5 computers. Okay, we did this on 5 computers and told everybody that first try to go to computer number one, and there will be a one main folder, and there you will find these folders where you can store the stuff. In case this computer is not working, go to computer number two. There also you will find a folder, main folder, under which there will be these drives. Now, that's the model we prepared. So we did it for like 5 computers, all 5 computers having the same folder structure. Okay. So do you think there is something wrong with the architecture? Yes. Mamta says that problem could be that some drive would get full while some drive would not be properly used. Brilliant, brilliant. Yes, yes. There, keep your keep your answers coming. Mahesh says IO and bandwidth issues. Brilliant, brilliant. And we will face Mahesh Arora. So I think because there are two Mahesh in the class, so I'll call Arora as, I mean, Mahesh Arora. So Arora says that we will face network bottleneck, and taking backups will be a problem too. Brilliant, brilliant. Also, what we used to do in this kind of structure, we used to place two hard disks on every computer, and one hard disk was exactly copy of the another for the backups. So, do you see any problem with that? Yes, he's saying network traffic. Good, good. Viswa says in case of failure, there is no place to find the lost file. Brilliant. Brilliant. So in case of failure, what we used to do was we used to have two drives for single data, one mirror of another. All right. Prezi says the okay. Prezi says that you need software to manage so many copies. Good, good. And sorry, Prezi says performance. Yes says so you need software to manage the copies. Okay. Good. Now, Abhay's point is network traffic to synchronize between the two nodes will be the issue. And also, we are not synchronizing between the two nodes. Okay, we used to say that drive 1 will contain the data which is starting with all the movies starting with go to drive 1, all the movies starting with B, some kind of a network map so that we don't have to synchronize. Okay. All right. All right. So his point is in case one node loses data, network traffic would be there to synchronize between the nodes. And that will be an issue. Right. Good. Very, very great set of answers. All right. Good. I think almost all of you have covered the issues with it. So first issue which we face is the failover and backup. There is a difference between failover and backup. Backup is that in case of loss, we have somewhere to go to. Okay? In case of loss, we have somewhere to go to. Okay? And and in case of that is backup, as in we can manually recover the data. Data is not lost. Data is there, but we are not. But in case of failover means in if something fails, there is somebody else who can take care of the same responsibility. Okay, so that is failover. Now this model does neither provide failover nor the backup. Although I was telling you that every drive is backed up, okay, but drive is not the only source of error. What if the computer is out of the network? What if one computer is having OS related problem? Or what if what if the what if the network connectivity of a computer is gone? So there could be many possibilities why a drive is not available in the network. Okay, so not only the hard drive. So when we create the backup of the hard drive, we only defend against one problem in case there is a problem with one particular hard drive, right? So and we did that because we only faced mostly the biggest challenge we faced was drives used to get corrupted. So we do have kind of a backup, but we don't have failover. So so effectively it will be fairly useless to people, because if a computer goes down, somebody has to go there and move the drive to some other computer, and then only it will be available. So this kind of system is not much available. How would you distribute data uniformly? Okay, so that is another challenge. In this kind of, every drive is behaving like an island. And so we create generally kind of a mapping, and this is a common mechanism. These are network file systems, or you can say that network attached storages. So when the when one folder fills in, you will have to move to another folder, right? Also, figuring out what is where is always a big issue. So the distribution of data is not uniform, and it's very difficult to locate where what is where. Maybe you could create a software layer where you will keep uploading the data, and that data will be moved to various hard drives. But again, that requires building something, right? So is this the best money for is this the best value for money? Is this the best use of resources? We might have hundreds of smaller hard drives lying all around, right? Here we have talked about, we have taken 1 TB hard drives, hundreds of those, and connected. If we had taken the old hard drives or existing hard drives from the network, the chances of their failure is very high, as well as it'll be difficult. The network will be far more bigger than this one and will be difficult to manage. Okay. Now, what about increasing availability? That is very important aspect. Imagine this. Today is Independence Day and everybody wants to watch the same movie. So everybody is trying to watch the same movie, and effectively the computer or the hard drives holding that movie will crash, because hard drive or the hard disk drives are a physical device. Physical device, when I say, there's a physical movement there's a physical movement of the header of the hard drives every time a user wants to access something. Okay, and effectively when people ask for too much of data, the header moves. Okay, the way you can imagine hard drives is like your old tape recorder or old cassette player, where you put the cassette and the reel goes from uh, reel keeps on moving under the header. So instead of reel moving, here it's the header as well which moves. So hard drive also rotates and header also moves in order to read the data. Okay, so hard drives is limited by how fast can it rotate and how fast can the header move. Header moves horizontally while disk rotates uh, in a circular fashion. So So when there are many people asking for the same movie, what would happen is the header would keep on jumping all the time, trying to cater to multiple users, and effectively it won't be able to do the justice to any of the users, right? So it cannot cater to more than two users or three users. So it'll be impossible to serve to more than two to three users. So effectively, most of the users will not be able to watch the movies if all of them are trying to access the same movie. Okay, so so uh, availability is not there. The accessibility is not there. Okay, and scale out. What does it mean by scale out? Scale out means today you have the requirement of few TBs. Okay, today you have the requirement of few TBs. Tomorrow you might have requirement of few more, and therefore we need to scale out. All right. So that's the okay. So that is about how, I mean, that's how we can handle. So these are the challenges. These are the challenges of the traditional system. So that is where the HDFS comes into play. Okay, that is where the HDFS comes into play. Now, so one thing was decided in the previous screen that if you have to store hundreds of terabyte data, you need to have you need to have you need to have hundreds of hard drives. And to have hundreds of hard drives, you cannot connect hundreds of hard drives to one computer. Okay, because uh, because every motherboard has a limitation. All right, every computer has limitation, and they can generally connect up to say 10 hard drives at most. And even if we connect it, the speed at which we can read from hard drives will get slowed down if there are more hard drives in a single computer. So we used many hard drives in many computers, so that is very clear. The second problem which we faced was that to locate what data is where. So we were talking about creating a central server containing the information about which file is where. That is exactly the idea behind name node. So HDFS is made up of two kinds of node. There is a single name node. Sometimes we call it admin name node, and then there are data nodes. So this name node on the admin node or name node is responsible for storing this metadata. That's exactly they did in HDFS. That's exactly they did. They created a machine which where everybody makes a note that okay, this file is going to be on that computer. Okay, everybody makes a note of this file is going to be in that computer. So that is name node. Now, so this name node keeps the data in memory so that when the users come to ask, hey, can you give me this file or can you tell me where is this file? Name node can quickly give an answer. All right. And all of these name node or data nodes are are services running on various nodes. Now the data node is only responsible to store the data. And where does data node stores the data? In the local file system. In the local file system. So in the local file system in the form of normal native files. Okay, inside a hidden secret folder on the same hard drive. So that's what it does. Name node. So it's basically HDFS is a high level file system which survives on the existing file system. The way you have NTFS and then you have HFS. So it survives based on the native file system. All right. So that's about name node and that's about All right. Now, next point, which I want to make it very clear. So, the second problem which talked about was distribution. How do you divide the data uniformly? So, when you have the files, some files will be really large and may not fit in the remaining amount on one hard drives. And therefore, you might have to move it to another. And you will eventually have many, many, uh, you know, gaps in the hard drives. Say drive 1, we try to store a big file and we realize that it has only left with 3 GB space while we want to store 4 GB. Okay, so we'll go to another hard drives. Now again, and those kind of problems will occur on all the hard drives. So the distribution of data is not uniform. So it was decided that whosoever is storing the files, they will split the file into the block size. By earlier, or I think in Cloudera still, so in some the default block size in some cases, say in some HDFS storage is 64 MB, and in some it's 128 MB. We will stick with 128 MB. Also, after you've installed HDFS, you can change the default block size. Okay, we have set it as 128 MB. So the files are split into a chunk of 128 MB. Okay, so if you have say 129 MB, how many blocks will be there for 129 MB data? Two. That's right. The first one will be 128 MB and second one will be 1 MB. So 1 MB will be 1 MB. All right, it won't take a space of more than 1 MB. All right, the second block will not take more than space than the actual required. So so basically, when you're trying to store a file, the file gets sliced into the blocks, and these blocks are handed over to data nodes, and data nodes store that. Now this is a very clever mechanism. It it basically made it possible to use older or smaller hard drives. Okay, you could store older hard drives giving you 40 gigabyte of storage, and you can utilize that for storing 80 gigabyte of data, because you'll cut the 80 gigabyte file into small portions and distribute it. The other benefits of cutting the big file into small blocks is it leaves less unused space on the disk. It optimizes the data transfer. Okay, it distributes the load to multiple machines. All right, Mahesh's question is who splits the the file into these blocks? Okay, so so to avoid these manual hassles of splitting and joining, okay, there is something called a driver. Driver is a utility on your side, on the user side. So user asks this command that, hey, I want to store the file. This command talks to name node and tells name node that, hey, I want to store this big file. Name node tells that, hey, please split your file into blocks and send the block 1 to data node 1, send the block 2 to data node 2, and so on. Now, once you have these smaller size files, it optimizes the transfer. Transfer as in case you want to move the data from one place to another. So there will be multiple computers involved, and effectively the overall transfer is going to be far more optimum. Also, the other benefit is when you append to the file. Okay, when you append to the file, only one block will get updated. When you append to a file, only one block will get updated, and therefore not the whole file is being rewritten. This also distributes the load to multiple machines, meaning one file is basically located on multiple nodes. And effectively, if let's say there is a huge video of 1 GB, now how many parts will be there for 1 GB? Quickly, how many parts will be there for 1 GB? How many blocks? Yeah, that's right. There'll be 8 blocks for 1 GB, and 8 blocks can be located on multiple machines. Now, this 8 blocks of a movie, say, imagine this, that there are 8 computers involved in it. So, first block on first computer, second block on second computer, third block on third computer, and so on. So, while the person was watching the movie, which falls in the first block, okay, let's first 15 minutes of the movie will be in one computer, second 15 minutes of the movie will be in second, and so on. So a user is loading multiple computers instead of only one computer, and therefore the overall throughput will be higher. So let's say you started watching the movie 15 minutes before me, which means you will be on the block 2 while I'll be on block 3, block 1. So and so on. So many people are watching the same movie without being the without blocking each other or crowding each other. All right, there are very good questions. Let me take the questions. First question is, does name node keep track of sequence of blocks? Yes, it does. So name node keeps a note of which block is on which data node, okay? Which file has been broken down into which blocks exactly in what sequence, okay? And and what is the block size, and so on. Okay, so that's the duty of name node, keeping the track of this metadata, as in which file got broken down into which blocks are lying on which IP address or which data node, and so on. Now there's a question from Mamta. Once a file is split into blocks, can it be changed while appending files later on? It can only be changed by appending. You cannot, if you try to alter the file in case of HDFS, it is more like deleting the old file and creating a fresh one. The same model as it happens in your local file system. In local file system, whenever you modify the file, it basically is rewritten to the disk. Now, Mamta's question is, can the block size be changed later on? Yes, it can be, but it will be like, again, it will be equivalent of rewriting the file again. All right, the block size can be changed. All right. Now, Mahesh's question is, do you have a screenshot or picture to show how it keeps track of data on of different sizes? Okay. So, all right, let me try to we will show you some metadata, and that will give you an idea on how to do it. Okay, let I can do a quickly. There'll be a screen afterwards where I'll show this. All right. Now, yes, his question is, name does a name node become the bottleneck? No. Whenever the request is coming from the user, Name node is only redirecting the user to the data node. Okay, now your botheration would be that why, when I want to just access the data, why would I? Okay, okay, so let me just close my, uh, all right. All right. Yes. So what if no name node fails? We will talk about these things in detail. That is a full 4 or 5 slides I have prepared, and various mechanisms to avoid name node becoming bottleneck or having the name nodes backup. All right. So basically, name nodes keep redirecting us to the data node. So imagine this. So imagine this. So we have got this nice. This is our name node. Okay. You are here, and let me. This is you, and you are asking, let's say, the driver. This is your driver. The driver means the command with which you are asking for any file. So you ask the file to the driver, say, give me the file. Okay, this is the name node. Okay, and this is your driver, and let's say this is you. Okay, so you are asking create file. All right, create file. Now there'll be these data nodes. So data node 1, data node 2, and data node. I'm drawing them from different sizes because every data node can have different. Okay, this is 1, this is 2, this is 3. Okay, now driver goes to the name node asking where should I store, where should I store file. Okay, so it tells that go to. Okay, go, and let's say create this file is say 200 MB. Okay, so here the name node will tell store first part in one, data node 1, and second in data node 2. Okay, that's what is the response from the name node. Okay, that's what it has replied. Okay, so now the name node has responded with this information. I have a more detailed this thing. Now at this point of time, what will driver do? What will driver do is, okay. So what will driver do is it will go to data node, okay, and store the data, store the first part, then it will go to data node 2, then store the second part, right? So this is the chain of sequence. So you started with creating 200 MB file, and which means name just told you to split it into two parts, 128 MB and other is how much? 72 MB. Now, uh, the driver goes to the data node 2 and stores the data. So it's the driver who is doing the heavy lifting on your behalf. It's more like a proxy for you. Okay. So Mithili's question is name node will be at client machine? No. Name node is a service and it will run in a network. These are all name node and data nodes all are part of the Hadoop cluster. Okay. They constitute the Hadoop cluster. So Hadoop cluster constitutes these components. You as a user could be on any of these machines or could be outside the machine. All right. All right. So does that make it simple? Next is next question from Mahesh is, does this store to data node happen sequentially or asynchronously by the driver? So what does driver do is it stores the data onto multiple nodes in parallel. Okay. How and where 200 MB data get splitted? So this command call, this driver, this the driver which is running at the same machine as you, okay, is responsible for splitting the data into this. Okay, or you can say if I mean it doesn't even have to split if you think about it. All it has to do is read the same file at different location. Okay, first from 0th byte it sends to data node, and from the next byte it sends to the second node. Okay, so so basically the driver, what driver will do is it will read your file from the beginning till 128th byte. It will 128th megabyte, it will copy the data to data node 1, and afterwards it will start copying to this one. So effectively it will the create the parts or the blocks as it goes forward. As a Hadoop developer, do I need to worry about name node? Yes, sometimes you do. Okay, we will talk about it. Who tells the driver about the block configured in the Hadoop cluster? It is the name node that tells. That's why here when we say first part, it will also tell that first part should be of this size. Okay, very good question, Biswa. All right. So that was about the blocks. Now there is one more piece of architecture which is very important. Every block, this was the problem which we faced earlier when we talked about the usual how we used to do things, the backup and failovers. Right. So now let's have a look at it. Each block in data node has multiple copies. Okay, each block in data node has multiple copies. Each so each block I would rather write each block of data. Okay, each block has got multiple copies. Okay, and this is called replication factor. By default, when you install HDFS, by default this replication factor is set to 3. Again, this configuration is stored in name node. We configure name node because name node is the one who is going to guide the whole cluster. Okay, so we say by default it is 3, but sometimes if you feel that 3 is too much, you can bring it down to 2, but I do not recommend it. Okay, because we are slicing a file into blocks and there is a disaster. In case one block is lost, the whole file is lost. If okay, and that's happening with almost every file, right? If there is a file, there are 10 files spread over 10 clusters. Sorry, spread over 10 data nodes. If one data node goes down, all 10 files will be wasted because their blocks have been lost. Therefore, it is strongly recommended to have a replication factor of 3, because in case two data nodes, if we had replication factor of 2, if two machines containing both the copies die, your data has gone. All right, and that's very much possible. The probability of that happening is very much possible because we have we have sliced the file into blocks. Okay, so so there is a replication of each block over the cluster. No two copies of any block is on the same node. Every block, every file is split into blocks, and every block is replicated thrice. And these copies are never on the same node, because if they're on the same node, we are still on the same disaster as we talked about in the previous design. Because the only thing it defends against is it doesn't defend against actually anything. If there is one file, if there are backups on the same hard drives, it doesn't defend against any disaster. Therefore the copies of the block are on different machines. All right, now this also gives us an added availability. Multiple people can now watch movies parallelly. So first, accessibility was improved by splitting the file into blocks, and second, accessibility is improved by having multiple copies of the block. So now minimum number of people who can watch a movie parallelly is 3. Okay, even if they start at the same second, they will be able to watch, 3 people will be minimum able to watch the movie parallelly. If you see that there are more than 3 people who are trying to watch the movie, all you need to do is you need to pre-prepare yourself and increase the replication factor. And sometimes some of the file systems such as Cubol's HDFS, what they have done is, based on the load that is coming from the user, they keep on scaling it up. Okay, they keep on increasing the replication factor. All right, now what if one of the data node fails? If your node fails at any point of time, the blocks which are lost due to this data node failure will be regenerated. Because how will they be regenerated? From the other copies of the block. It's not really lost. It's not really lost. It is there are 2 more copies left in the network. And immediately before any further disaster happens, it will start copying the already available block, so that in case there is further disaster, you still have copies. So out of say 4 nodes, you had the copy on first 3 nodes. Now the moment the first node is dead, the copy is done on the to the fourth node. Okay, so I hope that is clear. Now let me just try to show you. So let's say there were 4 data nodes. Okay, and you had your block. So let me just put some symbol. So you have one data here, here, and here. Now after some time, what happened was this data node went down. Okay, the data node went down. So what it will do is it'll copy the data from one of these nodes into here. Okay, it's the same file, and we will have basically the copy here recovered. All right. Now, what if we were about to copy the data and suddenly this node comes back? So in that case, it will not keep this file or delete this one, and just ensure that it is the same block as us. All right. So that was about the replication. All right. Now there's a question from Medili. Question is, if we have 2 blocks to store 200 MB, can we use rest of the second block to store some other data? If you have, yes, yes. So what happens is, basically, if you think about a block is actually a file in the local native file system. The way data node is storing data is in the form of files. every block is a file for data nodes. I'll show you when you go to the data node, there is a folder designated in the data node where creating creating the files for each data block. Okay, so first block will be 128 MB and second block will be say 72 MB, right? So this there'll be two files, some random number and called BLK. Okay, in all right. So effectively, all I'm saying is that since every block is like a file in the local file system, and the second file is just taking 72 at 72 MB. Therefore, it leaves a space for others. All right, good question. It's a very common question. Now, next question from Mamta is what could the approximate replication factor of Netflix be? Okay, that's yes. So they'll have actually multiple level of caching because it's theirs is a read-only data. So I was reading a paper from the people who do the streaming. They do many layers of streaming. So most likely it'll be dynamic. Okay, most likely it will be dynamic, as in when the demand grows, based on the demand, it keeps on increasing the replication factor. Okay, Prezi's point is that is it possible that three replications fail at that time? Yes. Okay. Let's say there is a data center and there's a fire in the data center, right? So all three replications can fail at the same time. All right. What happens when if the node that's down is up again? Good question. So in case it started copying to the fourth node and immediately it came back, which means it is back. So now it is in the choice whether it should continue this or uh, delete this. Okay, so it will basically delete the one which is smaller after comparing. So it will compare by hashing. So every block has got a signature. Okay, every block has got a signature, and as and when a data node connects back, their signatures are verified and checked that every block is intact. And once it is ensured that node is back and that the blocks are in the intact shape, then name node will have a, I mean then the name node will have a choice whether to keep this one or this one. So if generally the one which is full will be kept, so this will be deleted and it will be continued like this. All right, so based on which one is which one is in the complete shape. Now there's a question from Biswa. Question is, node 1 fails and the copy of file starts from. Okay, all right. So his question is one step ahead. So his question is that node 1 failed and we started copying onto node 4, and in the midway node 1 came back again. So so node 1 came back again, and so we removed this fourth file and then again went down. So shouldn't we be retaining this file? So I mean there are many such cases, and that's why to keep the design very simple, what they have done is they are basically whenever a node is joining back, the data is reviewed and the replication factors which have been there, if there is a replication factor of 3, the fourth one is generally deleted. So while deleting, it's not generally decided which one to delete. Instead, it's generally the one where the data is not completely copied that gets deleted. Okay, so they'll be little complex to handle such kind of scenario, and these will be more like, I would call them pre-optimizations. All right, these will be too much of pre-optimizations, but good point actually. All right, all right. So that is the HDFS replication. Now, the other point is the bottlenecks. Okay, we all asked about bottlenecks. So first we talked about name node and data node. Name node stores the metadata. Metadata means, again, a quick something I missed. Metadata means name of the directory, what is the block size, how many replications are there, and where are those blocks and their replica copies. All of this constitute the metadata. Name of the directory, name of the file, size of the file, how many blocks are there, what is the block size, where are those blocks, where are their replications. So this all constitutes to be the metadata. Now you can, when you think about metadata, so for each file there is going to be good enough metadata. So also keep in mind, if you have a smaller size block, then there'll be too many blocks and effectively there'll be too much of metadata. Okay, so it's generally preferred to have a bigger block in order to have lesser metadata, and it generally and not too big a block that most of the files are only having a single block. Okay, all right. Now this is what we imagine, because we all come from a background where there have been server and client architecture which has been taught to us. Okay, and the layers of abstraction and whatnot. So this is the kind of thing, when we think about name node, this is the kind of model which we always think about, but that's not true. This is not how it is. The architecture is not like that user will come and ask name node will talk to data node and gather all the data and give it to user. No. If that has been the case, what would happen is name node's network will always be busy and will not be able to cater to more than one user at any point of time. Okay, so and therefore this architecture cannot work in case of the data becomes bigger or the users become bigger. So and also in this model you are just keeping the name node busy, but therefore this is not the right architecture. The right architecture is this. So the user who is like me and you will use a command called Hadoop FS. That is the driver. Or if you are a developer and you are developing, say, a video streaming website, you will write a Java program, or you will write another uh, another layer of code which will talk to name nodes and data nodes. Okay, so mostly we will use the clients like your driver, or a command like Hadoop FS. Okay, so the driver, when whatever actions you want, it goes to the name node for consideration, and name node suggests the various things, and then it goes to the actual data node to read the data. So if you are just looking for the list of files in a folder, who will be talked to? So if this user, which is you, who is looking for just the list of files in a folder, it will go to the name node, and name node will tell, okay, this is the folder and it contains these files. That's it. This information is available with the name node. You don't have to go to the data node for this. Okay, but in case you want to read a big file which is already there in the HDFS, so a combination of name node data nodes is called HDFS. So when you want to read a file, your client will go to the name node, and name node will say that, okay, this file is available on these data nodes. go to them and get the data. So actual data reading and writing is done between the driver and data node. It doesn't happen through name node. Otherwise, you can write you can write the data as fast as your name node is, and name node will eventually become the bottleneck, right? Okay, so this is kind of a little ugly diagram, but yes, it is useful. So the client does the metadata operations with name node at every point of time. And the metadata always looks like the name of the file, number of replicas, and the block ID and all of that. Every block has got a big identifier, big unique identifier, so that at any point of time, it is possible to locate the block. Okay, now the client reads the data from the data node. The direct operations are happen always with the data node. Okay, whether the client wants to read the data or write the data, they generally talk to each other. Also, keep in mind when we talked about replication, now your question would be, who will do the replication? Will it name node? Will name node pick the data from each data node and put it on another data node? No, the replication is done amongst the data node themselves. Name node just instructs the data node telling, hey, why don't you copy this particular block from that node and keep a copy of it with you. Okay, and once you are done with the copying, let me know. So that's the kind of conversation that happens with name node. Name node says that, hey, I'm very busy, I cannot do your data operation, but every metadata operation has to go through me. Every operation, such as whether you want to delete a file, I need to be informed. Whether you want to append to a block, you want to create a file, you want to read from a file, i I am the authority, I am the single point of contact for the metadata information. Okay, all right. So Mahesh's question is, can I get the list of all unique files and their sizes in the HDFS store? Yes. A quick answer is use Hadoop fs minus du and minus r. Okay. This will give you the list of all the files, okay, with their sizes. All right. Now there's one question. All right. There's a question from Mamta, good question. How does the name node decide which replica to read from? This is an interesting question. How does the name node decide which of the replica to read from? So first, there are two criterias. First, the replica which is not much the replica from node which is not much in use. Second, the one which is nearer to the client. So these are the two criterias. So since name node knows the architecture of the network, we configure it. We configure something called data localities, and we represent the whole network as a tree in Hadoop. Okay, so that means that distance between every two node can be computed by traversing this tree quickly. The whole network is represented like a tree, not a graph, but a tree. So we can, at any point of time, we given two nodes, we can quickly tell the distance between a node and another node. So so based on that, the client can read the data from the node that is nearby. All right. So the first criteria is the node. So since everybody, whenever people are reading the data from name node knows that what all files the access is coming for. Okay. And it accordingly gives the priority list to the client, and client can further go and read the data. All right. I hope I have answered your question. Yes is saying, can you explain how does the replication work? So, all right, let me try to do. There is a few more bits I will try to inform you. So, the network is made up of two kind of computers. Sorry, a data center is made up of racks. Okay, I'll take it to another dimension. So your data center looks like big racks. One big rack, another big rack, and another big rack. Okay, and these big racks will have computers in them. These are your computers. Okay, like this. All right, looks good to you. So you can think of the first rack having three data nodes, and second rack having two data nodes. So this is rack one. So in a data center, you generally have these nice racks. The idea of a rack is basically one, a placeholder for the computers to save the space. Second, these are connected to each other here. So all of these nodes are connected to each other. So like this. So here, here, and here. And similarly, let's say this is also connected. So all these computers are in a single network. So these are all connected, and now they are connected together. They are connected together to say a master node. Here, this is our router. This is our router. So this is our router, and these are our local network. So each rack comes with a built-in place to plug in the cable, so that all the computers on the rack become part of the network. All right. Now, now here the transfer between this computer and this computer is faster as compared to transfer from here to here. Okay. So while copying the data, these things are taking into account. Okay. So when a user, let's say you are a user, you are logged in here, let's say on this computer, you created a copy here. Okay, you created a copy. This is where you are writing. This is where you are continuously writing your data. Okay, so the first copy of the data is generally on the same node from which you are writing. Now from here, the second copy will go on the same rack. So on the same rack as in here, and third copy would be off the rack on the second rack. Okay, why? Because if there is something wrong with rack 1, you have a copy available on the rack 2. Okay, and why both copies on the same rack? Thing is, when the user comes to access data here, and this node is not available, it is easier for the user to go here rather than here. So these are the nitty-gritties of how the replication work. Make sense to you, Yash? What is the size of rack? Racks come in various sizes, all right? And racks are also interconnected, as I have showed you here at the top. These are interconnected, okay? I'm not great at drawing, so I have to, how can I, all right, let me just delete it. So these are all interconnected. All right, they are all interconnected. How many data nodes can we have in rec? It's very custom, it's like saying how many sections do we have in an almirah. Okay, every almirah could be different. So rack is most likely just a word. There are many kinds of racks, and most of these racks are designed, custom designed in for every organization in every kind of data center. Okay, some have their own carpenter, some they buy. All right. So yes. All right. So that's about. I hope I have answered your questions. Now moving ahead. This is the same thing which we have talked earlier about. So there is an HDFS client who wants to create data, who wants to create a file. HDFS client is somebody who is working on your directions. So this HDFS clients first talk to the distributed file system, meaning HDFS, meaning name node. Now, when the client tries to create a file, it goes to the name node, creates a file, and then and then it gets the okay. So HDFS client talks to the distributed file system to create a file. It goes to the name node. Name node makes a note of that there is somebody trying to create a file, marks something called a dirty read, and then tells the client that hey, go to data node, write the data there, and once you are done with writing the data, inform me back. If the client doesn't inform name node back, it will discard the file. Okay, so the name node would wait for the confirmation from the client. Okay, so and also if somebody else is writing a file already, or this person is writing the file right now and another user comes in, this name node will tell no, you are not allowed. Okay, because there's somebody else already writing the file. All right, so those are the complexities of handling such kind of thing. Okay, Mahesh's question is Flume Scoop a HDFS client? Yes, they are HDFS clients. They are basically using the library of HDFS client. All right, good. This diagram is clear to everybody. Now, if the user is trying to read a file, it'll go to the distributed file system, get the locations of the block, and once it gets the location of the block, it will go to the actual data nodes and read the data parallelly and then assemble it. All right. Now, it was a very well-known issue that name node will suffer from the situations of single point of failure because name node is trying to be the authority or is an authority on metadata, meaning there are no two copies and there is user's request is always going to name node. So even if there are a million users or 10,000 users or 100,000 users, all of them talk to the name node. What happens when name node fails? Okay, and that's where the idea of the idea of the idea of the secondary name node comes into play. Okay, so name node stores data into two places. The metadata goes to local storage as well as network file system. Okay, that means in case local storage goes down, there is a network file system where it is stored. So it will basically, you can configure name node to store the namespace image as well as edit log. What does it mean by namespace image and edit log? Namespace image means from time to time, name node will take the snapshot of data and push it to the disk. that is called namespace image. And as and when new changes are coming from the users, it's appending to the local disk saying that, hey, I've got a request for creating this file. I've got a request for adding this file. I've got a request for deleting this file. Now those are edit log, and from time to time it'll consolidate the namespace image and edit log. It cannot keep on preparing the whole namespace snapshot because that is totally inefficient. Therefore, so those are namespace image and edit logs, just like having snapshots and new changes. So this metadata, this namespace image and edit logs, both are stored both can be stored on on local storage as well as the network file system. All right. Second is to keep a secondary name node. Keeping a secondary name node. So the secondary name node is a computer which will be brought up by loading the metadata. Metadata means namespace image and edit log. So as you can see that although we have backup, but we don't have failover. Okay, secondary name node is a backup but not a failover, meaning we basically uh, secondary name node will have a copy of metadata and edit log. So when you boot secondary name node, you will have to do it manually, and you will have to consolidate the namespace image and the edit logs. All right. Now the name node part is Now, still, these things do not solve the problem. So, these were the various attempts done by NameNode guys. This was the design of HDFS 1.0, that let's keep the metadata at two places, or let's keep somebody called secondary name node who is almost ready, and we can basically update. It will have the metadata updates. We will just bring secondary name node by combining the namespace image and edit logs. But this was not something which solved the problem. The real problem was solved by something called HA, high availability of HDFS. In the high availability of HDFS, there is the name node keeps informing the standby, and data nodes also keep informing both the persons, name node as well as the standby. So data node as well as name node both keep on updating standby. So standby is like a cold somebody who is waiting with all the metadata ready, and as soon as name node goes down, suddenly all traffic gets routed to the standby. The client or the user does not notice that the name node has gone down. Okay, so using Quorum General Manager, we basically make this happen. By default, in the design of HDFS, it was staged that every name node can inform other nodes as well for every changes. Similarly, it was also changed in the code of data nodes, in the logic on data nodes, that you have to inform all other standby nodes. Okay, so this way, even though name node is still a single point of contact, all the users are coming to the name node, but we have failover. These were these two approaches which we discussed in the previous screen. These were backups, while this is failover. We have standby just ready to be to serve the request, but it's not serving the request. We have failover, but still there is a chances of single point of failure. What if name node goes down, or uh, I mean, not what if name node goes down, name node gets so many requests in a second. How will name node cater to such kind of requests? Right, because name node is still accepting all the requests, and the reason which name node puts down is that, hey, I don't want any inconsistent consistencies in the network. I need to be informed about every change. So still, name node is single point of failure. All right, or name node is not highly available. Okay, not as in how should I explain? So if there are thousands of requests, the name node will die. Okay, and so will standby. All right. So here in this scenario, there is Mamta's question: how often does the backup happen? So this the snapshot happens in around a minute, while the edit logs happen immediately. A question from Mahesh: how does the client know it should call standby when name node is down? Brilliant question, Mahesh. All right. So I'll try to explain this. Uh, All right, so let me try to do a crosshair snapshot. All right, here. So this is name node and standby. So generally, the let me try to put it here. Zookeeper sits here. Okay, Zookeeper sits here, and name node and standby both are informing the Zookeeper. Okay, this is your client. We will talk about Zookeeper in detail. All right. So don't worry. And there are some ideas which I'm right now talking. So we might look that we are slipping or we are delaying, but we are not. All right. Every class is different and questions are always different. Therefore, I need to make sure that I answer your question. Otherwise, you will lose interest and there'll be no point of teaching. All right. So that's why I'm trying to answer all the questions. So, okay. So the client always talks to a service like Zookeeper. Zookeeper is the single point of contact. So the client goes to Zookeeper, hey, who is the current name node? Zookeeper tells, okay, this guy is the current name. Okay, this guy is the current name node. After some time, name node goes down. In that case, Zookeeper makes standby as the current name node. Okay, so whenever client is coming, Zookeeper will tell, okay, I only have one person's name right now called name node. Who is this one? So that's it. So Zookeeper does the switching. Zookeeper is basically highly available whiteboard as in name node wrote its name and standby wrote its name on the Zookeeper. After some time, as name node's name faded and name node did not refresh, that means name node is dead, while standby kept on rewriting its name, and therefore its name is still existing in the Zookeeper, and therefore Zookeeper knows that standby is up. So both name node and standby need to keep informing Zookeeper continuously every second that hey, we are up. Otherwise Zookeeper will think that that particular node is dead and will start rerouting the traffic. So that is the beauty of Zookeeper. All right. So Zookeeper is the way how most of the highly available systems work. Zookeeper does only this kind of works as in make things highly available or make the coordination between such kind of services possible. All right. All right. Next question from Biswa is: if the name node is in NFS, in which circumstances it will fail? Okay. I did not get. So name node is in network file system. Oh, If the name node is a network file system, in which circumstances will it fail? Mm, there are many circumstances in which network file system can fail. The network is down. I have seen the cases where the mice bit the cables. Okay, and so there are many circumstances in which a name node can fail. All right. All right. So there are many scenarios where name node could fail. Name node could fail if there are so many requests coming from the users, and here it. I mean, there are all kinds of scenarios in which a server can fail. All right. Network fluctuations, and hard disk crash, and CPU get burned out. All right. All right. Now, yes, Jesse's question is something very important. His question is name node some high-end server? Generally, name node is capped as little more high-end because name node keeps most of the data in memory. Now, since it keeps in memory, therefore it has to have a bigger RAM, and that is a very important criteria. So even in our case, if you see, I'll show you quickly. All right, I'll try to show you quickly. Okay, so the name node is on this one, 33. Okay, and if you go to the details of 33, you can see that this one is having 16 gigabyte of RAM. Okay, while rest of the nodes are having 8 gigabyte of RAM, this one is having 16 gigabyte of RAM. All right. So you can see that the name node is generally a little more high end. I think we have also the differences with number of cores, and you can see still it has got the higher average load. Okay, all right. The other, yeah, you can see that it has got 8 cores while others have 4 cores. Okay, all right. So let's take a quick break, and we will talk about HDFS Federation after some time. All right. All right, so let's start. All right, is everybody back? Should we start now? Great, great. Now, so the first thing which we discussed about alleviating the headache of name node was to have a backup of the name node in the form of secondary name node. And second thing which we discussed was having the standby. Standby is something which was introduced in Hadoop HDFS 2. Second version 2.x, 2.0, or you can say 2.x. Now, there was one more interesting thing that was done in HDFS Federation. What if the metadata which we're trying to store has filled the name node? Now, what will the name node do? What should the name node do in order to mitigate such kind of scenario? So that's where that's where the federation came into play. Okay, so in case of HDFS federation, there are multiple name node. Okay, multiple name node utilizing the same pool of data nodes. If you have 100 data nodes, both name node 1 and name node 2 will use the same set of data nodes in order to store the actual data, while the name node is has become 2. All right, some part of the data is being taken care of by the name node 1, some part of the data being taken care of by name node 2. Now, who does the switching between name node 1 and name node 2? This switching is done by the client library. The client library also got upgraded, and this client library got something called mount tables. So the client library maintains or reads the configuration from a central location, saying that slash and any request for the top level folder called my data 1 goes to name node 1, while the request for my data 2 and my data 3 would go to name node 3. Okay, so basically the idea is to divide the load of name node into multiple name nodes. This actually helps in order to provide a more availability. Second, provide a bigger metadata, because you cannot keep on increasing the memory beyond certain point of time. If the metadata is, say, taking more than 200 gigabytes of RAM, it will be difficult to go beyond 200 gigabyte. Therefore, the only option that is left in case of such huge data or so many number of requests is to go for the federation. This is called a federation model. Multiple name nodes serving to different folders, and and using the same pool of data nodes. Okay, using the same pool of data nodes. Yes. So the Yashi's question is, so the client library also has a metadata. Yes, client library has a config. Client library, when you use it, will read the etc config folder and will route route your request to the corresponding folder. So let's say you said Hadoop fs minus ls. Okay, you said ls slash my data. The request will go to name node 1. If you said ls my data 2 or my data 3, the request will go to the name node 2. Yes, Biswa's question is, so they serve disjoint set of metadata. Yes, that's right. Yes, his question is, so there are three metadata copies now. Okay. So there could be why three? No, this does not keep any metadata per se. Okay, this does not. It just keeps something called mount tables. This mapping between folder and server IP address. Folder and server IP address. I mean, name node IP address. That's all. That's a very small configuration. It does not store, the client library does not store any metadata. All right. It only keeps a mapping between this folder name, meaning if a user is asking for a file inside this folder name or anything to do with this folder name, the client library will the redirect the request to name node 1. It's like you yourself, you created in an organization that, hey, I have created two HDFS clusters. Okay, two HDFS clusters, and we have two name nodes. In case you want this data, go to this name node. In case you want this data, go to that name node. So instead of manual, this is done via the client library. Make sense now? So client library, it does not, is basically a command. It is basically a command. Okay, I will show you that. I'll give a demo after this. That will be better. All right. Yes, the information of my data 1 is not stored in name node 2. And similarly, the information about slash metadata my data 2 and slash my data 3 is not stored in name node 1. All right. So, okay. So, client library could be is basically a command. Okay, command which is having all this logic embedded in it. So, client library does not run anywhere. Okay, it is basically run by the user. It does not keep on running automatically. All right. Now the question from Yash is, in case of failure of name node 1, will my, will my folder 1, okay, okay, so in case of failure of name node 1, will make my folder 1, my data 1, right? That's what you mean to say? Yeah, my data, yes, that's correct. In case this name node goes down, it goes, it is dead. That is why there is a switching between here and here. This is the secondary name node. This is secondary standby. This is standby 1, standby 2. Okay. So it will start switching from here to here. Okay. So it will start switching from here to here. How do I? I think I will. Yes. So the moment it goes down, it will switch to the standby. Make sense to you now? If I'm looking for a file, then I have to scan all the name nodes until I find the file. Yes, that's a very valid point. Yes. If you're looking for a file, you will have to basically use the same command. It's the client library which will look through the my data 1, my data 2, and my data 3. But if you look at it closely, client library can also go a step further and and make it parallel searching in name node 1 and name node 2. Okay, so in a way it is better to search for a file, provided this logic is absorbed by the client library. All right, so lot of dynamics is being absorbed by the client library. Because if you do most of these things on server, then again that server will become the bottleneck, and that's how most of these dynamics with distributed computing happen. Wherever there is a work of switching between the two, is done by the client library. Okay. All right, again a quick look at what is name nodes metadata. The metadata contains the entire metadata in the memory. So name node contains entire metadata in the RAM, in the main memory, which means that the name node is generally the memory intensive game. Second is on-demand paging of file system metadata. So name node has the on-demand paging of file system metadata. What does it mean? It means that it keeps putting the metadata from time to time into the file system. Okay? There are many things inside metadata. One is list of files, list of folders, list of blocks of each files, and list of data nodes for each block, and then attributes like and list of copies of the blocks everywhere. Now, the file attributes such as access time, replication factor, file size, file name, and directory name. Okay, and then is a transaction log. So transaction log is also part of the name node, but it's not in the main memory. It is kept in the disk. Okay, it keeps the transaction log in the disk. So name node keeps track of overall file structure and the placement of data blocks. Okay. So Mahesh's question is, where is the metadata for client library stored? Client library stores its metadata in the metadata. Since client library is not generating any data first, it is just reading a configuration file. So this mapping of the client library will be kept in a config. All right. So that's pretty much good. So this is how name node data looks like. All right, let's have a look at something nice. Let's try to upload some data. Okay, so let me also try to log in into my account and go to Hue and go to Web Console. So we had a look at the Ambari. Ambari shows the so this is the how this is the system that would look to the the administrator. So administrator takes care of this UI. So you can see that the overall status of your cluster is shown here in the dashboard. Also, other than showing this, it makes it possible to restart and do all kinds of config changes to, to the various components. So I'll try to show you the size of the block somewhere. So if you go into advanced of HDFS, it should show you the size of the block. Okay, since I'm not administrator, it's not letting me change anything. I can log in as administrator, but it will be too risky right now. You can see that there was so you see, you can see that black block replication is also marked in. This is the default block replication. Okay, this is the default block replication, and there was a place. There was a place where it mentions the size of the data block. Yeah, you can see that. This is the DFS block size. And what is this? How much is this? This is basically this is in bytes. So these many kilobytes, these many megabytes, and you can see it's 128 megabytes. You see that? Under advanced HDFS site. So this is the configuration of our HDFS. All right. So that was our admin way of looking at it. So it provides you all kinds of reboot and install. So all you need to do is, if you want to add one more node in the cluster, all you need to do is, here there'll be a button called add node, and you can click on the add node and add that IP address of the machine, and that's it. Okay. You just have to provide login password of that node and it will install everything on that node. So CloudX Lab is something which we own. All right, these are our own setups. We provide to many other players in the industry who are using our cloud labs as a white labeled solution. All right, some of the industry people use our CloudX Lab. All right, this is our HDFS. If you go into file browser, this is our HDFS. My HDFS is having this data. I've already copied some of the data, and let me try to show you which file should I pick. So there was a user yesterday. Somebody has copied the data in his folder, and that was 130 MB. I was waiting for. So he has uploaded the whole video of the session in the HDFS. Okay, so I was looking for that one, my data. All right, let me just pick up any file for that matter. All right. So you can create your own folder and try to experiment on uploading. And then we will see, let's say in SSS, let's just pick up this part. Okay. This is the absolute location. Start the every file in Unix as well as in HDFS starts with slash. The slash has got a folder, then got another folder, then another folder, and this is the file. All right. So we can simply copy this location and go to our Veti. Let me reconnect to the Veti. We forgot to log in. Okay, yeah. All right. So here we are. Now we can use a Hadoop. We can use a command called Hadoop and fs to talk to HDFS. So it will show you the same folder structure what you see here. What you see here. Okay. All right. So you can see that you can interact with HDFS. So when I said a quick question to all of you, this command which you see on my screen, this command which you see on my screen, the one which I've selected, Hadoop fs minus ls, did it talk to did it talk to I'll did it talk to name node, data node, both, or none of the above? Okay. So this command called Hadoop fs minus ls talked to name node, data node, both or none. Yeah. All right. So yes, it talked to only name node. Why? Because it only needed metadata. This is all metadata. Okay. This is all metadata. But okay. So that's what it is. And similarly, let me ask you, if I say mkdir makes a directory in HDFS. Okay, you can use these commands by prefixing Hadoop fs. Okay, and these all commands are talking to HDFS. So my question to you is, Hadoop make directory, this one talks to who? Yes, Abhay says both. Anybody else? That's right. It only talks to name node. Okay, it only talks to name node. Why? Because the name of the folder is metadata. It's not data. The name of the file or the name of the folder is metadata. Okay, so folder you can always think of as if it's a part of the name of the file. It's not something which is data. It's not data. name of the folder is metadata. All right. So in both the cases, it is metadata. All right. Now when I clicked on this file, when we went here, we were here and we opened this file called part 0. This file is in hdfs. All right. This file, you can see the folder structure. This file is in hdfs. Okay. So you can see that this is what, this is a file which is staying in hdfs. When I open this file, then okay, or the same thing can be done from the command line, saying cat, let me copy that location, and the location is this. Okay, so all right, you can see this. All right, so you can see that we were able to print the data that is lying in this file using Hadoop fs-cat. Make sense to you? Now, this particular command, you know, this particular command, reading the file from the HDFS, is talking to name node, data node, or both. Yes? So Mahesh, this is a full file. Part 00, don't go with this name, okay? It's just the name of the file. It's not block number. Yes, it is talking to both. Because when it says, give me this file, this is basically going to talk to HDFS name node and tell that, hey, can you tell me, do you have this file first of all? If you have, can you tell me where is this files blocks? Then it returns, says, okay, this is just one block and it has got 3 copies. You go and read from either one. Now, let's say we want to check out how many actual blocks are there for this file. All right, for that you can use a command like this. Okay, let me try to create the command here. So hdfs, there is another command. So most of the commands are here. Okay, so you can check what all commands are there by saying hadoop fs and enter. Okay, so it shows you all kind of command you can append to a file. You can get means print the data, and there are all these commands. You have all the permissioning inside the hdfs. Okay, so here you can see minus help. Okay, here you can also say, if you say hadoop fs minus fs, okay, let me ask quickly this teaser question. So now Hadoop fs minus help ls, is it talking to name node, data node, or both, or none? Yes, this is talking to none. That's right, Mahesh. Good, good. So yeah, I just it is just a teaser question, and just to check whether you are listening to my question or not. All right, good. So everybody is saying none. All right, so I'm underestimating you. All right, now let's try to see the blocks of this file. Right. So Atul, I don't have a file with the size more than 128 MB. So you can try one big file. Okay. We have enough space on this cluster. Okay. We have enough space in the sense that how much space do you have? It must be something like it's only have 100 GB. No, no, it's 1.1 TB remaining. Okay, so we have 1.1 TB in the cluster. Okay, so you can try uploading few this thing. The only Downside of using hue is it's really really slow. Okay, so what you can do is I was trying to execute this command. Okay, so here we are. So all right, now let's try to have a look at this command will show us the number of blocks available. So HDFS FSCK, FSCK means file system check, minus blocks, minus location, minus rec, minus files. And this is the file which you are looking for. Here you can see clearly here, as you can see here, it says that connecting to name node via this particular URL, as in it's basically talking to that name node. Here this is our name node is running on a port called 50070. Name node is nothing but a service listening at a particular port, and this client is doing nothing but talking to this particular service, and is telling the name node that, hey, I am looking for this user ID, block number 1, locations 1, and racks 1. So sorry, I'm looking for blocks, locations, and racks and files, as well as the path called, this is the path, this is the encoded path. Now the response it gets is FSCK started by this person from this IP address for this path at this. Okay, now here you can see that it shows that there is only one block. Okay, there is only one block of these many bytes. After that after that you see this here. After that you see it here. This shows the block ID. This is the block ID. You see BLK. This is the number which is representing the block ID. Okay, and it shows that there is a replication factor is 3, and it is located in this rack. This is the representation of this computer in with respect to the network map. It shows that the this is the rack and this is the IP address. Okay, all right. This is the name of the data node. So it has got 3 copies. It has got this particular block has got 3 copies. One in this, other in this, and other in this. Okay. So these are the 3 IP addresses out of all the nodes it is storing in these 3. Also note that when it says talks about data node, it also tells you that there is an IP address, there is a rack, and there is a port number. The port number on which the data node is running is 50010, and 50070 is the port at which HDFS runs by default. Okay, so you can see it shows that it is healthy, and it also shows you the other aspects of it. All right, now you could do things like Hadoop FS. Now here, this file, we can do a couple of things with this. We could say Hadoop FS set replica as 5. So it's changing the replication of this particular file. Okay, now it has copied it on the 5 data nodes. Okay, it has copied it in the 5 data nodes. All right, so this is the block number. Now what happens, let's just do some crazy things. Let's try to increase the replication factor to 15. Okay, it says replication factor set, but under the hood what happens is, under the hood it says that target replica is 15 but found 6, because 6 is the total number of data node. It cannot do the replication beyond total number of nodes available in the network. Why? Because it restricts one copy to one node. Okay, it restricts one copy to one node. There's a whole idea behind it. Sounds good to you? All right. So that was an example of changing the number of replication factor. Now again, we can again change it back and set it to say 2. We are very confident about our cluster, and we just want 2 copies. Now rest of the copies out of it will be deleted. Okay, now it says healthy. Earlier it said no, it's not. And earlier it did not. Okay. Now also please note that here it shows the average replication. Okay, average replication means how many blocks are replicated divided, so total number of copies of the blocks divided by total number of blocks. Okay, total number of distinct blocks. So those kind of details are in this HDFS FSCK. All right, so you can try all of this and find out about the details. All right. Now that was a quick overview of HDFS. Do you have any questions to me at this point of time? All right. One more thing. Please note, please note that when you say LS, we are talking to this particular computer. There are 6 computers A, B, C, D, E, F, which are running the cluster. There are 6 computers connected here. These are the 6 computers which we have bought and on which we are running the Hadoop cluster. Okay, so we first installed Ambari on one of that Ambari server, this particular thing which is running right now. First of all we installed this machine on one node, and then this Ambari has installed everything on the cluster. Okay, so we have 6 computers running. And right now you are talking to the one with the 81. And which one is this? I don't know. This one is this one. Okay, the 81 one here. So this particular node called 14.81 is basically one of the computers, and it's a normal computer, and this computer also have some hard disk, and this hard disk is part of it is local to you and part of it contains the blocks provided by the HDFS. So I can show you that if you go to where, and if you go to where does it store, okay, where local, let me just see, I've forgotten the location. So basically, in one of the folder hidden somewhere, it is storing the blocks which are designated to this one. Okay. So Hadoop, let me see what is there. HDFS data current. So in this folder on this local machine, this computer on one of the machines, this is where it is storing the data. Okay. You could go into this particular folder and see that it has got the, okay, so you can see there are many folders inside it, and you can see that it has created its own substructure. Okay, under these it's keeping the data which you are uploading to HDFS. Okay, it has created its own internal structure here. Here is your block. Okay, and you can see tail minus f. Okay, so uh, okay, so it's a very small file. This is another block. Okay, So there is only one file which is, oh, there is one block. All right. So there is some block which is 128 MB. All right. So you can see that this is where it is storing the files. Okay. It has created some internal folder structure where it's keeping the data. So it's the local machine. I was explaining to you that at the end of day, HDFS uses the local native file system, and it creates one file per block on these machines. Okay, inside it, this is the actual storage of block. The question, like, we I have only 1 point I have only 312 bytes of data. What happens in this case? Or I have 93 MB of data in a block. Will it consume 128 or will it consume only 93? That is very obvious here. It's only consuming 93 MB space in the file system. Okay? Yes. So the question from Mahesh is, can we change the number of replicas from the client driver? Yes, that's what we did when we said Hadoop fs minus set replica, right? When we ran that command earlier, I'll show you this command which we did. Yeah, here. This was the command which we used to decrease or increase the number of replica sets. So, a question from Mahesh is, does HDFS store data in compressed form or standard? It provides you the facility of storing data in compressed form. Okay, it is completely okay with that. Okay, what is metafile here? Metafile here is some metadata provided over the same block. Okay, it some provided over the same block. This is the metadata about the block which it is storing somewhere. Yes, using Java driver also you can change the replica factor. All right. Can a HDFS have hybrid file system like Linux and NTFS? Can HDFS have? Yes. So, okay, let me repeat. What does it mean by Biswa? Biswa is saying, what if we can connect multiple kinds of node, one running Linux and other running NTFS, and we can have the HDFS. Although theoretical and as per the initial design, it was acceptable, but as of today, I am not able to add different kind of nodes in the same cluster. Somehow, the Hadoop cluster as of today is not allowing different kind of native file systems. Okay, although theoretically it was possible. Okay. So question from Yash is, if it is compressed, it will take the less than actual size. But the downside of a compressed file is that whenever you need this file, even if you need first 20 line of the file, you will have to uncompress the whole file. Correct? And those kind of challenges occur quite often when you have blogs. Therefore, HDFS provides you the choice of using compression, and the compression such as the compressions which provide you the data splitting techniques, as in, even if the data is split, you can uncompress the parts of the data. So those kind of compressions are part of HDFS, but it leaves the choice to you. Okay. All right. So okay. So Mahesh's question was that what is the need of a compressed need for compression in HDFS? Yeah, there's a need of compression because if you imagine that, so whenever you're storing data from say Apache web server, and what does data contain? Most of the data is fairly repeated. 100 gigabyte of file of Apache logs, a web server logs. Logs are error messages, information, and all of that. So 100 gigabyte of error messages, if you compress them, they actually become less than 10 gigabyte. Okay, so that because it's a plain text and there's a lot of repetition in the text and so on. So for these kind of scenarios, people have come up with new kind of compression called LZO. LZO is a compression where parts of the data can be independently compressed, or a compressed file can be split up and still you will be able to decompress it. That is the beauty of new generation compression such as LZO. The question from Biswa is, you are able to see the contents of the file. Isn't that a security threat? It is actually. It is. Okay. And generally we are not able to see the content, and that's what is surprising to me. I think one of the admins was going through this and was trying to fix the permission. So it's a minor mistake on our end. Generally, slash Hadoop folder does not have does not have permission for the end user to access it. Okay, so let me make a note of it. Thank you for reminding me. Okay, thank you for reminding me. Let me just make a note of it. All right, very great set of questions, and yes. All right, so we can copy, just explore all the commands here and keep a distinction between local ls when we say ls and Hadoop ls. Okay, Hadoop fs minus ls means we are talking to HDFS, and ls means we are talking to this computer's file system. Okay, go through one of the mechanisms I've talked about. Okay, so we have also talked about the installation instruction using Ambari. You can do the basically you can go through this one, and if you are interested in setting up using Ambari, follow this documentation. And there was one more thing. Okay, yeah, there is one thing called file system explained. Okay, so here all I've tried to demonstrate is that imagine that we have three machines, one, two, three. This is my desktop and this is your desktop. If you are on Windows and I am on Mac, so you can use putty to SSH as well. Although these days it's not required, but still if you want. Now, to copy a file, you can either first copy into HDFS, and then if you want to bring it here, you can say Hadoop fs minus copy to local. Okay, you'll be able to copy the data from Hadoop file system to local file system. Okay, you'll be able to copy, let's say I'm trying to copy my data locally. So it has copied the my data folder to the local machine from HDFS. You can see that. So sometimes some of the configurations, say for example, when you are running the MapReduce program, you will have to have that in the local file system, not in HDFS. And therefore, you will have to first upload in HDFS from the browser and then do a copy to local. All right. So that way you will get the data in the local folder. All right. So we used three kinds of command. One is ls, normal ls. Other is Hadoop fs minus ls. and other we used as HDFS minus FSCK. HDFS minus FSCK are the commands used in the cases of in the cases of so HDFS command actually is only for the administrative purposes. Okay, so HDFS command, as you can see, is basically for various HDFS purposes. Like you want to do the load balancing, you want to uh, enable crypto HDFS encryption zones, or you want to do other kinds of administrative purposes. So in those cases, you use HDFS. If you want to upload, download data, change the permissions, read the data, write the data, append the data, then you use Hadoop FS. Okay. So Mahesh is saying, what tools are you using currently on Mac? So I'm using a text editor called TextMate. And what else am I using? I'm actually not using much. I'm just using the browser-based tools provided by CloudXLab. Okay, Web Console, which is browser-based console, and Hue and Ambari. Yes, we can also copy the data from local to HDFS by saying Hadoop fs minus copy from local, say sales.log. Okay, now sales.log will appear here in my home folder. Okay, let me sort it by the date. Okay, you can see that it has come here. All right, makes sensible to you? So go through the list of commands here. Go through the list of commands, Hadoop fs minus ls, or just type help. It'll show you all the details about all the commands. See that? Just go through the list of command. What all can you do from the command line? Okay. So every file here has got a permission, chmod, chgroup, cat, and all that. Okay. Good. Good. All right. So that was about HDFS. Now let's start the discussion on the compute engine. Do you have any questions at this point of time? Now, question is local file as in the file on your desktop, Mahesh. So the one I showed you, Hadoop fs minus copy from local. Okay, that will do the job. All right. And if you want to copy using, so from Veti, no. Okay. Okay. I'll just change your question a bit. Can I copy my local file as in my laptop file? Okay. The file on your laptop to HDFS using Veti? No. You will have to use two ways. Number A is copy the file using Hue to HDFS. Then after that, second step would be after you've copied, then you do Hadoop fs copy to local to bring it to the local folder. Okay. So yeah, but sorry. So you basically want to copy your file from the laptop to HDFS. One is this using Hue. Other way is you use WinSCP or you use SCP to copy file from your machine to a computer in network. So that's out of this, that is step number A. Then you do is open VATI. Then what you do is you run the command called Hadoop fs minus copy from local and then your file. Okay. So first you either use SCP. SCP will copy file from your machine to one of the nodes in the cluster. So you could say copy file from your machine to say what is that node, what is that machine name? This is E. Okay, e.cloudxlab. So you copy the file using SCP or WinSCP from your machine uh, to 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 e.cloudxlab.com. Okay, sounds good to you? And on Mac, you can simply say SCP. All right, it is already installed for you. SCP, your local file name, and then e.cloudxlab. Before that E, you have to say for me what was the login. My login was this. I will have to say things. Can I show you? So let me just open. This is my local machine. Okay, this is my local machine. So let me try to copy a big file. What is that big file? Let's say this is 113. Oh, I have really big file in this folder. Let me just try to copy this 13 MB file. Okay, so I'll say SCP. Okay, and the file name. This is the file name, and then I go ahead and say this is my login name. This is what happened. Why I'm trying this? So I'll have to go to my local machine like this. Okay, let me try doing that. All right, say SCP, and this is the introduction to big data and Hadoop. Okay, SCP, what was the folder name? Yep. I'm copying this. I'm saying SCP secure copy from my laptop, from my Mac onto e.cloudxlab.com into my account called Sandeep this. Now it'll ask me for password, and all I have to do is take this password from here and oh, it did not work. Sorry. I have to put colon after this. Okay, now it's copying the data from my laptop to the server. Okay, so I'll just make a note of it to all of you. So this is what I'm doing on my Mac. And if you have WinSCP, WinSCP will give you the beautiful UIs, and you just have to mention this server name there with this login and the server name. That's it. Okay. So if you want, I can just send it to you. Alright, so that was how we have uploaded data. Now, this file, if you see, it appears in my local folder, but is not in my Hue, because this is what? This is my HDFS folder. Okay, this is my HDFS folder. So it's not there. It's in the e.cloudxlab.com. Okay, this is in e.cloudxlab.com. It's not there in this server. Now what do we do next is let's copy the data. So it has reached e.cloudxlab.com. Okay, all right, right. So here we can simply say either copy from local or move from local. Okay, that is, so we have a command called move from local, and it will move this file quickly to local. What URL syntax? Oh, it wants this file name to be something else, I think. Is it? Let me try to make x.move. Okay, and then Hadoop fs move from local x.movie. Okay, so it has moved quickly. So now it has moved the data in this folder. Okay, let's just refresh and see. All right, so this file has appeared here. All right, if you want to do the from the command line, if you don't like to upload from here, if you want to upload directly, you can upload. Otherwise, you will have to do SCP and then move. That's a two-step process. Now, uh, question. Okay, there was a question, and I think somebody has asked. Yeah, Abhay was asking that do we have a manual for all of this? Right now, I have not kept a separate manual for Hadoop FS minus help. Okay, have a look at it and also go through this diagram. Okay, this diagram. Okay, along this diagram, and along with that, you go through Hadoop FS minus help. Okay, that should give you a good starting point. Right. Good, very good. Now, instead of copy, we could use copy from local. Yes, that was very much correct. Okay, I just wanted to show you one more command. All right. So now let me just delete it. I don't need it, so I can simply delete forever. Mahesh's question is, can you create exercises with common Hadoop commands with examples to practice? Let me see if I can do that. Okay, let me see. I'll get back to you on this. Okay. All right. Yes, we'll do that. All right. So that was about our Hadoop HDFS. Make sure you try uploading, try creating these files, and try checking whether you can use it from uh, the web console, whether you are able to upload or not. So those all things you can do. Okay. All right. So next is the compute engine. The next idea which we want to go into is the Hadoop compute engine. All right, that is the yeah. So we will go one step at a time, and we will go into more and more details as and when it's required. All right. Just a quick question to all of you. If you have 1 gigahertz processor and you have to sort or order 1 terabyte of data, then then how much time do you think it will take? How fast can a simple computer sort 1 terabyte data? This terabyte data is made up of 10 billion strings having 100 characters each. You have 10 billion strings having 100 characters each. So you have to sort such data, order such data. And my question is not how would you sort? My question is how much time will it take? Okay? My question is how much time will it take on your machine? Good, good. Mahesh says it will take more than 5 hours or about 5 hours. Anybody else? An error of 50% or an error of 100% is totally acceptable. Okay, Mithili also says that it will take around 5 hours. So in general, even if you have multiple processors in the same computer, it will take close to 10 hours or maybe more. Okay, that too, what will you do is you will read data in parts. You will read data in parts and then you will sort it and then merge it. Okay, you will sort the data and then merge it. So it will take close to 6 to 10 hours. It'll take close to 6 to 10 hours. All right. Before I move forward, there was one more question which has been left unanswered. His question, Aroda's question is, so with SCP, first we need to copy the file to Hue, and then we can copy to, not Hue. Hue, when we say Hue, uh, it means HDFS, okay? So we need to copy the file to e.cloudxlab.com. All right, makes sense now, Mahesh? All right. Now coming back to why is this opening? All right. Coming back to it. So how fast can 1 gigahertz processor sort 1 terabyte data? It'll take close to 6 to 10 hours. Okay. Now what is wrong with this? We need faster sort, bigger data sorting, and we need it more often. Now, when we sort this data, mostly it is the hard disk which is the bottleneck. Why? Because reading 1 terabyte data itself takes around 5 hours. So, no matter what kind of processor you use, no matter how much memory you have, it will inevitably takes more than 5 hours because at the end of day you have to read the data. The only extra baggage we have is when you have a smaller memory, what you do is you first cut the data into smaller sections, sort the data in parts, and then save it. Okay, then save it. So okay, so that is how we generally sort bigger data using smaller RAM. Now, even if we are able to have 1 terabyte of RAM, which is impossible theoretically, okay, which is impossible. But still, let's just hypothetically say that we have a very big memory core of 1 terabyte, and we can load all of this data into the memory and then sort. Still, loading the data into memory take will take around 5 to 6 hours easily, because none of the disk IOs in a hard disk has improved. Okay, it'll still take 5 to 6 hours just to load. Computing will take another hours. Okay, that's why even in the best case scenario, you will end up beyond, maybe will close to 10 hours. Okay, so Mahesh's question is, so e.cloudxlab.com is Hadoop client. So it's not a Hadoop client, it's a node, it's a machine name. Okay, so Hadoop, we have 6 nodes: a.cloudxlab, b.cloudxlab, c, d, e, f. Okay, e is one of the nodes. All right, so Abhay's question is, what is the difference between node E and the cluster? Node E is part of the cluster. So when I say ls on node E, I'm talking to the local hard disk. When I say Hadoop fs minus ls, I am talking to the HDFS. Okay. Sounds good to you? No? All right. All right. Okay. So if you have any question, or do you want to try it now, guys? I can spend 10 more minutes, and we can do a hands-on with we'll discuss as- rest of things later. Can you all try to create your own files in your folder, and also upload your file in that and test it? If you face any challenge, I will immediately make you the presenter, and we can take a look at your problem. All right? Or you want to do it later and we schedule a discussion for 10 minutes or so? Okay. So if you want to try, you can try in next 1 minute, and then let me know. Okay. Instead of jumping into another topic right now, let's just try to do it. Okay, so this is the console. Try logging into console. Is everybody able to see this section in their cloudx lab? Okay, are you able to see this section in the cloudx lab? This section, you won't see the edit and all. Though don't click on the cloudx lab details, it is wrongly linked. Okay, so this particular section, are you able to see? And are you able to log in? All right. So I would say that everybody should try creating a folder, trying to understand the difference between local file system and the HDFS. Try to upload a file. Try to upload a file into HDFS. Try to copy a file to local file system. So three things we have three things here. One is we have three things. One is local file system of e.cloudxlab.com. Okay. B, HDFS. C, we have C, your laptop or desktop. Okay. So you should first upload a file to HDFS, upload a file to e.cloudxlab.com. Also, from A to B, B to A, C to A, and A to C. Okay, you should try these. Okay, or what is left? B to C. Okay, I think I should just say these things. Okay, so try these 6 operations. Okay, try these 6 operations. So, Bishwa, are you not able to log in into your account here? Don't you see my courses and don't you see this? Does it give you any error? So this is the CloudX Lab. You see these? Don't click this or this. Click on any of this. All right, so that's pretty much for today. Try, I mean, give all of this a try. Otherwise, it'll be a complete confusion later on because you will have to utilize, say, for example, when we run MapReduce program has to be here. Okay, while the files that MapReduce program processes has to be here. Okay, and so on. This is anyway something which is very clear to you. All right, so that's it. All right, thank you very much. Have a great day. Bye bye. All right, all right, bye bye. And yeah, so Abhay, could you send me the recording of the session after this? Okay, maybe you upload the recording into HDFS itself and I'll take it from there. Okay, thank you Abhay. Have a good day. Bye bye. All right. Thank you, everyone. Thank you, Atul, Biswa, Lakshmi, Mahesh Arora, Mamta, Methi, and thank you, Murli. Thank you, Mithili. Thank you, Prezi, and thank you, Yash. Bye bye. I hope you're having a good time. Feel free to get in touch with me. So the recording will be uploaded here. Okay, session 2. The recording will be uploaded in session 1, session 2, session 3, and so on. Right now you'll see old recordings, but I'll upload as soon as possible. So Biswa, can you send me the screenshot at Hadoop at No Big Data? I'll have a look at it. Just send me the screenshot. Let me take a look. All right. I think maybe something wrong with the account. All right. So we don't have a class tomorrow. We will see on the next week. All right. Bye bye. Have a great day. If you have any question, feel free to reach out. And I would expect that you should try all of these commands by yourself and make yourself comfortable. Make yourself comfortable. All right. Thank you very much. Have a good day.